All right. How's it going, guys? Hope you had a good weekend. We've made it to the last week. Week 6.
That's dope.
Wow, time has really flown by. What's up, Sibley? What's up, Fedekai? Yeah, so you guys took an exam on Friday. I think I saw on Campus Wire. People said it was... I don't think anything was like really like surprising, right? Nothing was like super... I've never seen that before. But yeah, I agree that some of the questions might have been lengthy. Let's see. I have the exam somewhere. Another 2 to check your... Holy shit, what? 8 hours? Why is that... I hope I'm not making the exam like that long. Is it really that long of an exam? It's only 12... It's only... What is it? 4 multiple choice, 4 free response-ish, and then like 2 big part questions. The end draweth nigh. I do, Zach. Okay. Oh, you check your work really thoroughly, though. Yeah. Yeah, I got you. Okay. The numbers being tedious. I agree. And again, I hate that the numbers are tedious, but that's unfortunately a byproduct of what we have to do with online tests. If it was in class, I would make the numbers nice so that you're not, again, like 0.33, like, you know, doing all the decimals and stuff. It is super annoying. I agree. But with how they have it for like the random numbers, it generates like some decimal, which can be annoying. Anish says, I think since it's open note, we take as long as we can to double check and make sure our notes align. Yeah, you are also going to be a lot more cautious. Yeah. Yeah, I get it. It's like, ooh, I got to make sure like everything's exactly correct. Yeah. The last 2 questions, yeah. Some people were complaining about question 8, which was this one right here, yeah. They said, wow, where did this one come from? This one was so hard. And I'm pretty sure I did this twice during 2 different office hours. The only difference between this question and the one I did in office hours is there's 1 extra capacitor here. That's it. But it's the same setup as everything else we've done. Question 8 was literally on the homework as well. Amelia, weren't you the one that asked me during office hours about this one as well? Yeah, exactly. There's just 1 extra capacitor in series. Yeah. Yes. Okay, Amelia. Well, I hope you got this one right, Amelia. Because, yeah, I literally did it during office hours. I did it twice. I did it 2 different times. Yeah. I mean, basically, you just say that this capacitor doesn't really matter. And then it's like 2 capacitors in series and stuff. Yeah. So... yeah, well, heads up. Yeah, if something you're like, oh man, that was difficult. Oh, where'd that come from? I probably did it during office hours. Again, I think this was on your homework. This is a very similar one to your homework on this. Let's see, this one, we kind of did this one. The infinite cylindrical shell. We've done this a couple times. This is a classic question, which I think I did during lecture. Yeah. We'll see. I think, what, percentage-wise? Yeah, it looks like question 8, only half the class got right. Question 10, 70%. Okay, cool. All right, we're looking okay. Oh, question 1 was tricky, too. 88%. Okay. Yeah. Well, yeah, I'm going to wait. So I got to go through and get these all entered into Brew and Learn. And then also, I think Albert's working on the solutions for it. So hopefully I'll have a grade to you guys either tonight or like early tomorrow for this. The line charge was counted for linear density. The line charge was just an infinite charge. I don't think there's not a volume density to it. There's a linear charge density for sure. Yeah. I feel like, yeah, it's okay. I know there will be regrade requests because again, Kudu gives you like all or nothing. It's either you get it right or you don't, right? Which I don't think is fair. So yeah, don't worry. We'll still have regrade requests. I probably am going to have to make the window a little short. I can't give you a whole week for it because the registrar is getting, very antsy about us submitting final grades. And also the next summer session starts, I think, next Monday. So again, if I was also teaching the next session, which I would murder myself if I'm doing that, because it's so much. That one starts on Monday. So they really don't give us much time to do stuff. What should we expect on the final? Again, I haven't written the final yet. I'm still grading your midterms from Friday. But my general idea for the final is to feature a little bit more heavily the stuff we've done in the last week. So like DC circuits, so like Kirchhoff's rules. Today we're going to do charging and discharging capacitors, so that'll probably definitely be on the final. Basically like the last 2 chapters of things that weren't on the last midterm, those will probably be more heavily featured on the final. And then we'll also have some throwback questions to stuff that was done earlier in the year. So, I mean, the final is technically cumulative, but it's more heavily weighted towards what we've done second half of last week and then first half of this week. It says yeah, it's okay. Yeah, Sib, it's fine. That's what the regrade requests are for, because again, Kudu, if you make like one little math mistake, it counts the whole thing wrong. And that's annoying, and that's not fair. So I will allow regrade requests. That's okay. You forgot to do the pre-lecture? What? You guys have all day to do the pre-lecture. But I get it. I mean, life is busy. There's a lot of things going on. Trust me, for me too. Even just as a professor, there's so many things. Like, I have to give a lecture, and then I have to make sure, did I get those notes uploaded? Okay, did I upload the syllabus? Or did I update the syllabus? Did I update the due dates on this? There's so many things, and it's happening so quickly. So I empathize with you being like, there's a lot to keep track of, but that's the summer course. It's not for the faint of heart. So, I mean, congratulations for making it this far. It's not easy. I usually, when I private tutor and advise kids and they ask me, should I take a math or a science course over the summer? I tell them no. I say, because it's brutal. It's very fast. But I understand that, not everyone has the same luxuries with timing and course selection. So sometimes you do just take a science course over the summer. But I usually recommend, go take a history course, or go take some literature course, something chill. If you're gonna take something over the summer, take one. Don't do OChem and physics, or don't do calculus and biology. You got to pick just one. I know some students that are taking OChem over the summer and physics over the summer. I'm like, wow, that is murderous. Yeah. Dun, dun. Linear algebra and physics. Yeah, that's brave, dude. That's really brave. Good for you, Fedekai. But I mean, I would not recommend that to people. It's difficult. If you made a small math mistake on the MCQs, could we ask for partial credit? I usually don't do partial credit for the multiple choice question because it's multiple choice. You get a 1 in 5 chance anyways. Also, I mean, a lot, and this is a thing I talk about in, I talked about this last quarter, but mainly because last quarter I was teaching pre-meds in 5A. I tell them that in your life there's going to be a lot of multiple choice exams that you have to take, because that's the only way they can standardize an assessment to the entire nation and not have it be ridiculously expensive to grade it. So this kind of all or nothing with multiple choice, you have to start getting good at now, because the MCAT the LSAT, even the physics GRE, they all have a multiple choice component, which there's no partial credit on it. So you have to get good at that. Yeah. Doing OChem and physics, am I cooked? Yeah, no, if the ones where you input a number, the numerical ones, I offer extra I offer partial credit on those. That's fine. And it's the same as the last midterm. We'll have regrade requests for that. So yeah, don't worry. Okay. Oh yeah, surveys. How are we doing on the surveys? Let me go check. Then here, let me start this off. Welcome to week 6, lecture 1. Okay, looks like for the surveys, we are currently at 66%. Ooh, that is close. So, remember, if we get to 80%, I think everyone gets like a 0.2% boost to their total grade. No, we're close. Look at this, 66%. Come on, guys. You have until... Today is technically really the last day, because this deadline, I think, is at like 8 a.m. PST. So, do we have until the end of the week for this? For regrade requests, I'll tell you what the deadline is for that. It'll probably be maybe the end of the week, maybe a little bit before that. But yeah, no, this is due basically the end of today. So if you have not done this, do yourself and your class a favor, you know? Go here, I'll post the QR code again for people. There we go. But I heard it takes like 2 minutes. It's very, very quick. So please do this today. There you go. If you want to scan that, there's the QR code. And then I think they have a link for it as well. Where's my link? There, I'll post the link in the chat. Yeah, Fedekai said, just brief question. The finals half the time as usual, but twice the number of questions. No, I'm not doing twice the number of questions. What? No. That's cruel and unusual. I think the final will be maybe like 1.5 times the number of questions. Not double. Not doubling it. But yeah, you don't get the full 12 hours to do it. Just again, that's just department policy. They take the finals like really seriously because the midterms are 10% of your grade. So if there's like some academic dishonesty, it's not the worst thing in the world. But if there's cases of people cheating on the finals, it causes chaos. So they kind of really want it to be, you know, within a certain time period. They don't want it to be easy for people to cheat. But not saying that you guys are. I mean, you guys are doing pretty well. I haven't noticed like too much like blatant someone's cheating. And, you know, I appreciate you guys being honest. And again, you're doing it for yourself. I always say, even if you cheat one of these classes, you're just cheating yourself in the future because you're going to get screwed in like 1C. If you don't learn what to do here, 1C is going to be really rough. So how long will the final be? I haven't determined that yet. But approximately, I would say between 1 to 1.5 times as long as a midterm. But even though the registrar says you only get 3 hours for it, I'm going to give you 6. So, I guess half the time of a midterm, but a midterm 12 hours is ridiculous. Like, no class in like the history of anything at UCLA will let you take an exam for 12 hours, like in person. This is just a kind of a byproduct of the online structure. I've caught some suspicious. Yeah, I've seen some like stuff. I'm like, that's sus. Like, there's some stuff where I'm like, oh man, that's kind of sus. Like, don't do that again, please. Because eventually, like, if they're blatant with it like twice in a row, I have to report it. and then it's a fucking headache, and it's a nightmare. I don't really want to do that. So yeah, that's why I say in the notes, I'm like, please don't do this. I don't want to have to go to whatever academic senate council thing. But yes, what's the difficulty jump between this and 1C? I would say it's definitely as difficult. I'd say it's slightly more difficult because you start dealing with magnetism, which is like can be tricky to like visualize. I've heard 1B is harder than 1C, but that's because Corbin is notorious for 1B. You know, poor Corbin. Yeah, no, 1C I think is a little bit harder because the magnetism side of things tends to be a little bit more difficult to visualize. Also, you're dealing with cross products instead of dot products. So all throughout this, we've mainly dealt with dot products for, you know, E.dl, whatever, lines stuff, yeah, or yeah, E.da, yeah, all that stuff is dot products. When you get into magnetism, now you start dealing with cross products. So for instance, Biot-Savart law is like dB cross R, and that can be hard to kind of visualize because now you're doing things in 3D. And then also, I think they start throwing in special relativity and optics. I hate optics. Optics is... I do not like optics. But, yeah, so that's why I say 1C is probably a little bit trickier. It mainly because magnetism is harder to visualize, and then optics is kind of a pain to teach. But, okay. Depends who's teaching it. So, again, right... Any class can be great or terrible, depending who teaches it. Zach, what? You had a final from 9 a.m. to 9 p.m.? That's nuts. What? Yeah, the grad students at UCLA are taking their comp exam, I want to say in the next couple weeks, and that's 2 days, and I think it's 6 hours per day. I forget. It was a rite of passage. But okay, so please fill out the set surveys. It takes 2 minutes. I'll make an announcement later today, also on Brew and Learn, just to really like try to corral people into it. But if you guys do this, everyone gets bonus points on their total grade. Also, in terms of clicker grades and everything, there's a homework due today at 2 p.m. Please do that. There is one final homework due Wednesday at 2 p.m. Please do that. And then tomorrow will be the last clicker for the course, because by Wednesday at 2 p.m., I want to start finalizing grades and putting everything into Brew and Learn for you guys. So we won't have any graded clickers on Wednesday or Thursday. And then Friday's the final. So, yeah, tomorrow's the last clicker you got to worry about. And then hopefully I'll have all your grades transferred over by Wednesday night. Again, it's fast. This is a very fast class. Summer is so fast. It's my first time doing the summer. I'm very glad I did not sign up for back-to-back sessions. I need a break after this. And then regrade time for the final. I need to check in with the registrar to see what the due dates are for that. But I will try my best to give you a decent amount of time to deal with it. So by Thursday, our grade will be finalized besides the final. Correct. Should be, yeah. Yeah, I hope by Thursday to have everything in besides your final. Depending how quick I can get through the regrade requests, there might be some of that lingering, but everything will be in Brew and Learn at least. Right now, you have your grades scattered between Brew and Learn and Kudu, and it's hard to tell like where you're at. Yeah, you're welcome. All right, today we're gonna go over charging and discharging capacitors. Do you want to sign up to teach 1C any quarter, please? If they hire me. I don't know. UCLA is going through some like weird budget issues right now, and so I'm like in the air of whether I teach next fall. I'm currently not scheduled, so maybe I'll let you guys know if I do. Apparently, there's kind of like some last minute things that happen, but I don't know. All right, charging and discharging capacitors. Please teach it winter quarter. We'll see. Anything can happen. Where's this on Kudu? Okay, cool. So charging in. So if we remember when we originally dealt with capacitors, probably like 2 weeks ago, we talked about like capacitors have some properties to them, right? So if you have something that looks like this is always like a capacitor. It's going to have some charge, positive Q on one end, which is usually where there was a positive voltage source. And then it'll have minus Q on the other end. And this is like some negative voltage source that's creating that. And then in between it, right, you have some capacitance, C. And that was defined as being the ratio of Q over V. So it's the ratio of like the amount of charge you can put on each of the plates and what voltage that, keeps it at. Now, capacitors, in order to get charge, have to have a source of that charge. And the source of that charge is usually a battery. So usually what happens is you have some positive voltage source here, V naught, that is connected. And what happens is current will flow from each end of the battery. Okay, so this will be like positive current. This would be like negative current, technically, or like current's coming away from here. And that deposits positive charge on one plate, and then it deposits negative charge on the other plate. Or really what it does is it's like pulling the positive charge away from it so that it becomes negatively charged. And this current will only flow as long as it needs to in order to get to the equilibrium state here, where you have enough charge on this plate that with the capacitance, you're also at the voltage of the source you're connected to. Yeah, there will be discussion. I will still have discussion Wednesday and Thursday. I think I'm planning on doing kind of a review for that. I'm going to do something. I'll look into it. I haven't planned that yet. We're finishing up capacitors today. Charging, discharging, and then tomorrow we're going to do some more advanced circuit stuff like ammeters, ohmmeters, and kind of more practical, like how like electric shock happens, why you ground things. And then Wednesday and Thursday, I haven't decided yet exactly what I want to go into. Maybe I'll have you guys vote what you want me to do. They're like, hey, can you just go over the final? Can you just do the final for us, Dr. G? But okay. So capacitors usually start uncharged. They're connected to a battery. The battery will deposit charge on the capacitor until it reaches its equilibrium charge that it wants at this voltage to equal this capacitance. If you kindly offer to do so. Right. So RC, and this is usually there is some sort of resistor in line here. Okay. Usually there's a resistor. And what that resistor does is it kind of controls how quickly this battery charges the capacitor. You wouldn't want there to be no resistance here, because then instantly this capacitor, this battery would just dump as much charge as it could, as quickly as it could, to fill the capacitor. And that can be dangerous sometimes. First of all, that high of current creates a lot of heat, and so you can start melting wires if you do that. Also, I don't think capacitors like getting shocked that quickly with charge. So usually what we do is we have like some sort of switch and then a resistor that kind of like throttles the amount of charge being deposited on the capacitor from the battery. And that's what's called an RC circuit. So right here, we have introduce the RC circuit. Introducing the RC circuit. When you take 1C, you're going to deal with RLC circuits. So that's resistors, capacitors, and an inductor. And then if you have this in like an AC circuit, RLC circuits do this cool thing where they oscillate. Kind of almost like a pendulum. It's really cool how like even things in electrical land follow the same behavior as what I would say is like mechanics land, of just, pendulums rotating back and forth. Same thing happens with circuits. Okay, so usually what happens is this is your original circuit, okay? Where, again, we have a resistor here, we have a capacitor here, we have a voltage source, EMF source, or like a battery, and then there's a switch. Okay, when the switch is in this position, it's open, there is going to be no current flowing here. So we're going to say, like, no current. Because the only source of current, which would be the battery, right, doesn't have a closed loop to go around. It stops here. It's just open. This is called an open circuit. Now what happens is we decide to close the switch. Okay, and this is now the equivalent circuit you get. In this case, now the battery is connected to the capacitor, and while the capacitor originally had no charge on it, so here we say like uncharged capacitor. Now, once we've closed the switch, charge will start to deposit on the capacitor, and that's because there is going to be current flowing from the battery. Okay, so this is going to end up, this has like, and this is usually like very high current is what it is to start with. And then as you start to deposit more and more charge on the capacitor, eventually the capacitor reaches its capacity and it no longer can take any more charge on it. At this point, the amount of current flowing from the battery goes to 0. So we say I eventually goes to 0 as like time goes on. And we'll show, there's an equation for this. Okay, now once the capacitor is charged, what you can do, and I don't like that they should show the rest of this circuit. They should, one second, let me pull this here. This is really what happens. So once the thing has been charged, okay, then what we do is we put the switch into another position here, okay, and that's going to create this circuit equivalently, okay, which is like this. In this case, right, the capacitor now has charge on it, plus Q and minus Q. It acts as a battery, and it will discharge the current in the opposite direction to try to neutralize itself. And this is why you want a resistor here, because you don't want it to instantly short itself right away. That creates like a bomb. So the resistor here will then slow down the discharging of this capacitor, whereby the positive plate here is eventually going to neutralize with the negative plate here, and you eventually get a capacitor that is uncharged again. And you may be asking, like, wait a minute, where did the charge go? Where'd the energy go? Like, because there was energy in this. If we remember that the energy of a capacitor, so energy for a capacitor is equal to 1/2 CV squared, right? That energy gets lost in the form of heat. So here we say, like, capacitor energy gets lost as heat through the resistor. Okay, so yeah, that's the typical, charging a capacitor. Well, you have an open circuit, you charge the capacitor, and then you hit another switch, and then you start discharging the capacitor. And you may be asking yourself, like, why do I care about this? Why do I want to do this? It turns out that this can be very useful when you have things that you want to, like, oscillate, like, back and forth. So the classic example they give are, like, they say intermittent windshield wipers. This is actually kind of cool. So this is, like, the example. This is, like, the real world example. And then we're going to go into the math of, like, how the charging works. So I don't know if you guys have driven cars or stuff. You may notice that when you turn on your windshield wipers, right, that they go, like, it slides one way, and then it slides the other way, and then it stops, and then it does it again. And there seems to be, like, we call this, like, a wait time, right? There's a time that waits for it and then it like does it again. This is done with a capacitor. So here they say a relaxation oscillator is used to control a pair of windshield wipers. So the oscillator consists of a 10 microfarad capacitor. So this is the capacitor, okay? And then they say a 10 kilo ohm variable resistor known as a rheostat, okay? So this right here, just as a little extra bit of knowledge, this is called a variable resistor. It's also called a rheostat. Another one for this is like a potentiometer and things. So this is always like kind of like a knob, and it's really cool. So what it does is, and I like how they do this for the notation here. What they're saying is that depending on where you place the connection point, right, from here to here, will determine the amount of resistance, right? So if the knob is like right here, then you have to go through the whole resistor to get over here. But if you like kind of shortcut it a bit, like if you connect, let's say, the wire here to like halfway through the resistor, now you only have to go through half the resistance. So variable resistors are ways that, again, if you ever seen, you know, with a light bulb like that dims, you know, or even like a volume knob on, you know, speaker system or something, these are all variable resistors, whereby you have some mechanical thing that is choosing at what point in the resistor to like start dropping voltage across it. I can probably get a picture of one of these. This is the classic variable resistor. This is obnoxious, but they use these for like really high powered systems. But this is an example of a variable resistor. So notice how you have like a lot of wire here, right? And remember when we talked about resistance, right? Resistance is dependent on the amount of length you have to go through. So what they do here is they move this top part here back and forth, and that changes how much resistance the circuit needs to go through before it goes from one end to the other. Yeah, they use these for, again, for cute little physics labs and also for very high-powered systems. Now, what usually gets used is a potentiometer. And this is kind of like a variable resistor. They physically move it. Yeah. You physically move that what was it? This part. Yeah. So, for instance here, do you see how there's like a black terminal here and a red terminal here? Okay. And then the black has to go through all of these coils to wherever it connects here and then comes back down through the red. So if, for instance, your knob here is way over to the left, then you have to go through a lot of resistance because you have to travel through all these coils and then come back. If this thing is closer here to the right, now the resistance is low because this doesn't have to travel as much in the resistor coils before like coming back to the red. So yeah, you can physically move this to adjust your resistance. I'm trying to see if there's like an easier one for it. Potentiometer might be different voltage. I'm pretty sure it's variable resistance. Yeah, no, it is. Yeah, but where's like the? I want a diagram of it. Okay, fine. Well, this is kind of what it looks like. If you ever end up doing circuits and stuff, this is kind of what a variable resistor would look like, and they use this symbol for it. But what happens is as you turn the knob, it changes like how far something has to travel through. Yeah, these are all cool little different things. Yeah, look at all these small ones. Oh, like the big knobs. Yeah. Anyways, so if you have, again, a circuit here where there's a capacitor, there's a resistor, and we'll get into this later, but the resistance here being variable will change how long it takes for the window wiper to like go back and forth. Usually, yeah, what they say here is that the output of the capacitor is used to control a voltage-controlled switch. The switch is normally open, but when the output voltage reaches 10 volts, the switch closes, energizing an electric motor and discharging the capacitor. And that causes the windshield wipers to sweep, and then once the capacitor is discharged, it then needs to charge again before it'll sweep again. So what they're saying here is you have a battery here, you have a capacitor here, and it's going to start charging it until there's a device here. This is the, let's say the motor and the windshield wiper. And when the motor sees the correct amount of voltage on this capacitor, it then discharges that, which causes the windshield wiper to go up and down or whatever. And then it waits for this thing to charge back up again before it wipes another cycle. So this process of taking time to charge the capacitor and then it discharges and having to charge it again, that's what creates a oscillatory function. So, and the cool thing here is the amount of resistance here determines how fast the capacitor charges. Because, again, resistance is kind of like resisting the flow of electrons. It's resisting current. So if you have a higher resistance, then less current is able to flow to the capacitor. Versus if you have a lower resistance, you have more current. And if you have more current, the thing charges quicker. And so the window shield wipers, they go back and forth faster. It is cyclical, yeah, exactly. Sensation, yeah. Okay, I mean that's why they're cool. But let's talk about the math of how long it takes to charge a capacitor. Because V equals IR, exactly, Sib. Yeah, right? Yeah. Yeah, V equals IR, right? So if this is set at 12 volts, if you raise this, you lower this. And if you have less current, you're going to charge a capacitor slower. Okay, let me find the math. Oh, very cool. Oh, so we can use some calculus on this. Yeah. Okay. Let's consider that I have here, let me put like a resistor here. I will still be here, Phantom, yes. Well, I hope I'm still here. I don't know. The world's crazy sometimes, but yes. Good luck on JEE. JEE stuff is nightmare hard, dude. Okay, let's say we have a voltage source here, which we can call like V0. And then we have a capacitor here with a capacitance C. And we could do by the loop laws, right? Let's say we start here and we want to like, and also remember you always have to define like what direction current is, right? So I'm going to call this as like, this is I. So by the loop law, if you start here, you would have V0, and then we would say minus IR minus the voltage going across this, right? Because in this case, the capacitor is positive and this is negative. And remember that if you're traveling, as you do your loop, as we do our loop here, if you travel across the terminals from positive to minus, that's subtracting. So this would be minus the voltage of the capacitor. And then this is equal to 0. And what we remember about the voltage across a capacitor, right? That's equal to Q over C, right? Q equals VC. So Q over C is equal to V. So now what I can write this as, I can say, okay, cool. Well, this is V0 minus IR minus Q over C is equal to 0. Now, current. Let's remember, current is defined as the change in charges over the change in time. So that's equal to dQ dt. Remember, because current is amps, which is like coulombs per second. right? Or amps equals coulombs per second. So, and that's a unit of charge divided by unit of time. So now we can say, okay, well, V naught minus I, well, instead of I, we're going to say dq dt. And then this is R minus Q over C is equal to 0. Okay? This is a differential equation because in terms of the variable Q here, I have the derivative of it somewhere, and then I have the, like, the 0th derivative, or just the regular variable somewhere else. So what I can do is try to integrate this by separating the variables. So I want to put everything with Q on one side and then everything else on another side. This is a trick from diffeq that you'll learn. So this would be dq dt times R minus Q over C. So let's see, what do I want to do? Oh, I want to put dt over here. Oh, I see. One sec. I want to do this. And then yeah, and then here, let's move the R over. Let me do this step by step so this isn't getting too complicated. Sorry, this is V naught minus Q over C is equal to that. And then I'm going to divide by R. So then I have V naught over R minus Q over RC is equal to dq dt. And then let's multiply this by C over C so that I can combine them. So now I have V naught C minus Q all over RC is equal to dq dt. I got it. I'm going to move this up here. I'm going to move this down here. So now I have dt over RC is equal to dq V naught C minus Q. Okay, cool. This is a little tricky with the algebra, but this is called like separation. Can I spell separation of variables? Because what happens is we have everything with Q on one side and everything with like dt on the other. Okay, now what we can do is we can integrate both sides. So I'm going to take this and I'm going to do an integral. Okay, and time, we're going to go from some time t equals 0 to some arbitrary time. We're just going to call like t is equal to let's say like t final. Okay, let's do that. And then for measuring charge, we know charge is going to start at 0, right? There's no charge on the capacitor to start with for dq. And then that's going to go to some q is equal to q final. Here, this is q equals 0. Okay. This is a simple integral. Integral of dt is just t. So I get 1 over RC. And then that's going to be just t evaluated from 0 to t final. Yeah, we'll see the frequency. The frequency does play into this at some point. Watch this. This is a little trickier. This looks like 1 over x dx. Where you have to say here, I have to say, okay, let, this is u sub. U equals V naught C minus Q. So then du is equal to negative dq. Right? This does not depend on time. Right? The initial voltage of the battery and capacitance doesn't, but this does. So now I can do this integral as the integral of negative du over u, which is the same thing as the integral of negative ln of u. Negative ln of u. Technically absolute value, but whatever. So this part here is going to be minus ln of whatever my u was, which is v naught c minus q, and then that's evaluated from 0 to q final. Okay, cool. Let's see what we get. I think we're getting close. So doing this, I just get t final over rc is equal to, so with the negative, I can just flip the signs of these. So that's going to be ln of v naught c minus the ln of v naught c minus qf. Okay. And then if you have ln's, right, of things subtracting each other, it's the same thing as them dividing. So I could say, okay, well, tf over rc is the same thing as ln, and we're going to say like v naught c over v naught c minus qf. And we're eventually charging, the whole goal of this is to eventually determine what q is as a function of t. We're trying to figure out q of t is equal to what. I want to know, what is the charge q on this thing at a time t? So from my differential equation here, I eventually want a function of q as a function of t. So I don't like q being on the bottom here. This can make things weird. So I'm going to take a little step here, where instead of writing them this way, I'm going to flip them. I'm going to do this and this. And then I'm just going to put a minus sign on here. So anytime you have like a minus b, you can turn that into b minus a, as long as you put a negative sign outside of it. So all I did is I multiplied both sides by a negative sign, so then I can flip this. Because now this is going to look better. Now this is ln of v naught c minus qf over v naught c is equal to negative tf over rc. And then I do e to the on both sides to get rid of the ln. So I'm going to do e to the. And then this will get me e to the negative tf over rc is equal to v naught c minus qf over v naught c, which is the same thing as, let's move this over here. So I get v naught c times e to the negative tf over rc is equal to v naught c minus qf. Okay, cool. I think I see where this is going. This is actually kind of cool. Move this over. So I get v naught c, and then that's going to be e to the negative t over rc minus 1 is equal to negative qf. So then, again, flipsies, we get that qf is equal to v naught c, and then that's going to be 1 minus e to the negative t over rc. Cool. Oh. So, yeah. This is saying, and how we write this is we say like q of t. So we say the charge on a capacitor at a time t is equal to v naught c. That's the same thing as like, we say that that's like q naught. So this is like the final charge on it. And then this is 1 minus e to the negative t over rc. Where this thing right here is equal to v naught c. Okay. I know. That was a lot. It was a lot we just did, right? But some cool things about this. Okay, so notice. Is something like this expected on the final? I'm not expecting you to derive this. No. This is just, it's a cool derivation. I just wanted to do it. You don't need to know how to derive it, but you need to know this. You need to know the final result. And I think it's also given on equation sheets usually. But some cool things about this is that, watch this, as t goes to infinity, right? This becomes e to the negative infinity. E to the negative infinity is the same thing as 1 over e to the infinity, which is equal to 0. So this whole thing goes away. So as t goes to 0, as t goes to infinity, you get that the charge on a capacitor is equal to the final charge that should be there, the V naught C. Yeah. And then also at t equals 0, right? If t equals 0, then you have e to the 0. This is 1. 1 minus 1 is 0, so there's 0 charge here, right? So as t goes to infinity, qt becomes q naught, and at t equals 0, you can say like, oh, q of 0 is equal to 0. So that's another way to just make sure that the math checks out. Is seeing, I call it like the boundary conditions. It's like the extremes. Like what happens right when I start charging the capacitor? What happens an infinitely long time after I charge the capacitor? Well, I expect after charging it for a while that the charge on the capacitor should equal the regular VC, V naught C that we get. And then at the beginning, the charge should be 0. So yeah, this is a cool derivation. Again, I'm not gonna make you guys do derivations in tests because it's, you know, it's kind of whack. But it does build a good appreciation for, you know, why the maths. Some cool things here. They also end up calling this. They end up calling this tau, which they call like the time constant. And what you should notice is that this thing here determines how fast or how quick the capacitor charges up. If you were to graph this, bigger R's mean that you need more time in order to get the charge to its final equilibrium position. Okay. So now that you have the charge, which, notice how the charge, right, goes from 0 to its final charge, like Q naught. You could also look at the current. I'm not going to do this derivation. It would take too much time with what we got in class here. But you can figure out what current is from dq dt, okay, which means now you're taking ddt of this whole thing. And what you end up getting is that the current is equal to what's called like the equilibrium current, or the current without the capacitor, and then it's e to the negative t over RC. So here we get like I of t is going to be equal to V equals IR, V naught over R, and then we say e to the negative t over RC. And this is also still charging. Okay. So that one's important, and this is also like important. Cool thing you should see here, right? At t is equal to 0, right? I of t, so I of 0, is just equal to V naught over R. So the current rushing to the capacitor is just equal to V over R, which is the same current through the resistor, right? Remember V equals IR. As t goes to infinity, though, right? Notice that you end up going to e to the negative infinity, and that e to the negative infinity is the same thing as 0. So eventually this just goes away. And so as t goes to infinity, the current goes to 0. So this is a cool thing. It's so capacitors start with no charge, end up with a bunch of charge on it, and they start with a ton of current running to it, and then the current eventually drops to 0 as, again, the capacitor reaches its maximum charge, It doesn't need any more current because it's already charged. And this is all just from math. That's why I think this is pretty wicked. I mean, from a conventional, practical point of view, it makes sense. As you're filling something up, eventually once it's full, you don't need to like keep filling it. But from the differential equations here and the calculus, you get the same like physical result from like a mathematical interpretation. It's really cool, I think. Okay. Turns out you can then also talk about the voltage on the capacitor, right? The same way. Which I think it's this one, right? Yeah, here it is. Yeah. So if you wanted to talk about the voltage on the capacitor, remember that Q is equal to VC. So Q of T is equal to V of T times C. So that means V of T is equal to Q of T divided by C. So now with this, you can say, okay, V of T is equal to Q naught over C, because you're dividing both sides by C here is what you're doing. And then it's 1 minus e to the negative t over RC. And so then this is just Q naught over C is the same thing as V naught. And so you get V of T is equal to V naught 1 minus e to the negative t over RC. So this is another important thing. Again, look here. So the voltage across the capacitor when time equals 0 is 0. And then as time goes on, this term eventually goes away, and the voltage on the capacitor is equal to the same voltage as the battery. And that's what happens. When you're charging a capacitor, this thing eventually wants to be in equilibrium and have the same voltage as this. And then by V is equal to Q over C, whatever that voltage is here, that then determines like what the maximum charge is that's on the capacitor. And it won't go over that. Yeah. Okay. This is all for charging. Then we have other equations for discharging. But they're really just like the opposite. It's just going in the opposite direction. To talk about charge time. Charge versus time. Yeah, here, yeah. These are all like the little graphs. If you wanted to see like a visual representation of where this comes from. So again, as you're charging a capacitor, right? Initially has 0 charge and then fills up. Current is initially very high, and then you no longer need more current to charge the capacitor. Voltage starts at 0, hits its equilibrium voltage. Oh, and this is for the resistor. Well, yeah. And then eventually, if there's no current going to the capacitor, that means there's no voltage drop across the resistor either. Ah, that's kind of cool. Okay. Discharging a capacitor is kind of like the same thing. So wait, this is for, did we just do here? This was charging. Charging derivation. Then you can have discharging, which I'm going to save you guys from doing all the messy calculus. So in this case, you have a capacitor that is again just connected to a resistor, and there is no voltage source anymore. The capacitor is the voltage source. Okay. So in this case, this has like some positive Q, some minus Q, and current will flow to eventually discharge it. It simply says what? What about what? So this is charging a capacitor. Yes, yes. Okay, because remember, Sib, that as you dump, right, charge onto the capacitor starts having its own voltage. Because it has positive charge here and negative charge here. So it has voltage. So if, for whatever reason, let's say you remove the battery and you just have the capacitor here, and then you have the positive end somehow connect to the negative end, current will flow from the positive charged plate of the capacitor to the negative charge. Yeah, you're good. And this was in the others, this was the circuit they kind of talked about. They talked about, oh, you know, I connect it here, it charges it. And then I connect it here, now it discharges it. Yeah. Turns out you can do the same thing with Kirchhoff's laws, like going around this way. And I'm just going to write down what the answers are, because I don't want to spend too much time slogging through math derivations for you guys. But this is what the charge on the capacitor is. So notice how the charge is going down, right? Because as t goes up, e to the negative of something that's up is then like something that's small. And so you can see here, like, as t goes to infinity, q of infinity is equal to q e to the negative infinity over tau. They're using tau instead of RC. This is RC. This eventually goes to 0, and so it's equal to 0. You can then take a derivative of that to get the current. So then the current is this. And then do they do the voltage? Oh. Well, I guess, yeah. By the same thing, by the same way we did it here, right? We said, where was it, right? Yeah. V of t is equal to q of t over c. So, if you want to just divide it. So, V equals Q. E equals... One sec. Double check, make sure I'm doing things right. Q over C. Okay, that's what it is. Okay. So, V of t is equal to Q over C e to the negative t over tau. But Q over C is the same thing as the voltage, the initial voltage of the capacitor. So we say like V of t is equal to V naught e to the negative t over tau. On the homework, there's no capacitor resistor combination. Are there not? Really? That's dumb. There's no RC circuits on the homework? Excuse me? Let me see. No, question 16. Yeah, question 16 has it. Yeah. And question 17. Yeah. Yeah, the last two. Yeah, I was like, I'm pretty sure I made sure we had some capacitor stuff in there. Yeah. Yes, question 16 and 17 in the homework have charging and discharging capacitors. But anyways, these are the important questions, the important equations you want to know. So this is the charge on a discharging capacitor. This is the current through a discharging capacitor, and then this is the voltage on a discharging capacitor. Yeah. Cool. Okay, let's see. I think there's some clicker questions involved with this. Let's go see. Okay, 20 microfarad capacitor has been previously charged up to a total charge of 100 microcoulombs on it. The capacitor is then discharged by connecting it directly across a 100 kilo ohm resistor. Calculate the charge remaining on the capacitor exactly 3 seconds after being connected. Okay, cool. So, I mean, this is a discharging question, right? Okay, so key thing, this is discharging. So we want to use our equation for charge for a discharging capacitor. That's this, right? And this is like the initial charge that's on it. So, all right, cool. I'll say this is 100 microcoulombs, e to the negative t. And then this is, well, they said after 3 seconds, so that's negative 3. And then tau is equal to RC, which in this case is 100 times 10 to the 3 times 100 times 10 to the minus 6. So, what is that? 100 times 10 to the minus 3, then? 10 to the 3, 10 to the minus 6, 10 to the minus 3. Yeah, cool. So then this is Q of 3, is what we say. So, you got to pull out your calculator for this one. So, I'm going to do everything just in microcoulombs, because all the answers are microcoulombs anyways. So, I'm going to say 100 times e to the negative 3 over 100 e to the negative 3. And that's going to get me 9.35. Well, one sec. Did we do this right? RC. 100 times 10 to the 3. Capacitance is... Oh, ooh, no. Sorry. I put the wrong number here. This is not... No, dude, no, this is the capacitance. The capacitance is not 100 microcoulombs. It's 20 microfarads. This is 20 times 10 to the minus 6. Okay. Thank you. Yes, thank you, Sophie. Making mistakes out here. My bad. My bizzles. Okay. Okay, so let's change this. So this is 100 e to the 3 times 20 e to the minus 6. Okay, so then that gets me 22.3. Okay, cool. So that's equal to 22.3 microcoulombs, which is answer choice B. Let's go see if that's correct. And it is. Oh, now they're gonna ask about the time. Ooh, okay. This is another one. They like this. Okay. 20 microfarad capacitor, again, has a charge of 100 microcoulombs on initially. It's discharged, same thing. At what point in time will the capacitor have 13.5 microcoulombs on it? Okay. So now instead of charging, instead of solving for how much charge there is, we're solving for how much time it takes for it to get to that amount of charge. So in this case, you're going to get 13.5 times 10 to the minus 6 is equal to 100 times 10 to the minus 6. And then this is e to the negative t over RC, right, which is 100 times 10 to the 3 times 20 times 10 to the minus 6. Okay. To solve for t, this is a classic logarithms question, okay? I want to, like, divide this first. I'm going to divide this over first. So, what's that? 13.5 divided by 100, because the 10 to the minus 6 is cancel. So that's going to be 0.135. Duh. Equal to e to the negative t. And then I'm going to say over this RC here. So to get the t down, what you do is you take the ln of both sides. It's a common trick we learned, right? So ln of 0.135. ln of that is going to bring this thing down. So you end up getting negative t over RC is equal to the ln of 0.135. Okay, so then just move it over, right? So now we just have RC ln of 0.135 is equal to negative t. So that's 100 times 10 to the 3. 20 times 10 to the minus 6. ln of 0.135. Nicing, ln of 0.135. This is going to be a fraction, so that's a negative number. So that's why we have negative t eventually happening. All right, so 100 e to the 3 times 20 e to the minus 6 times the ln of 0.135 equals that, and then take the negative of that, so you get that t is equal to 4. Cool. Was that an answer choice? Ooh, answer choice A. Nice. Is it answer choice A? It is. Okay. Cool. All right. That's it for today. I'll let you guys out a little bit early. I hope that made sense. I know there was a lot of long derivations there in the middle. Don't worry, you don't have to do those derivations for any sort of exam. I just think it's cool to see how the math matches up with the physical interpretations of things. And if you're interested in, like, again, pursuing physics beyond the 1 series, that's something you really want to get comfortable with. You want to get comfortable with using calculus, using differential equations in order to solve, you know, things. So, cool. If you have any questions about what we went over, I'll have office hours in about an hour. So at 3 o'clock Pacific, same place, YouTube. So come on by, ask some questions. Otherwise, I'll see you tomorrow, and we're going to wrap up the chapter with going over some ammeters and ohmmeters. How do you recommend practicing that? The best way to practice derivations is to, you know, literally start at the beginning. Where do we do it? Yeah. Like when I did this thing here. Yeah. Like start here and see if you can get to an expression for Q. And if you get stuck, you know, try to look at the derivation and, you know, only use it for what you need to get to the next step. But yeah, doing derivations is a very vital, important thing if you want to do physics, again, beyond the 1 series. So this is why they always say, like, this is an exercise for the reader. It's kind of like extra credit, like homework for you to just kind of practice on it. But you usually always know what final result you're trying to get to. So it's about practicing getting from the initial step to the final step. Yeah. Okay, cool. All right. I'll see you guys in office hours later today. Otherwise, I'll see you tomorrow. Enjoy your Monday. Peace.